Hello and welcome to our next lecture in CHY 113. Today we're going to focus in on the concept of the mole. The mole is a concept in chemistry that allows us to scale things up. Remember that when we talk about atoms and molecules, we're talking about something really, really, really tiny. And it's useful for us to think in terms of single atoms or single molecules when we're talking about maybe atomic structure, or if we're talking about chemical bonding and we're looking at one atom coming together with another atom, forming a chemical bond, or when we start talking about reactions later on and how some of those bonds are going to be broken and reformed, then we do want to try to visualize things down in the realm of single atoms and single molecules. When we start to think about the amounts of things that we might actually use in a lab, however, thinking in terms of single atoms or molecules doesn't do us any good. We're not ever going to go into a lab and measure out 10 molecules of glucose or 20 different NaCl, so 20 different sodium chloride units. We're never going to do anything like that because they are so incredibly tiny. And so the mole allows us to scale things up into terms and into amounts that we might actually be using in a lab. The scientific technical definition of a mole is that a mole is the amount of a substance that contains as many particles as there are in 12.0 grams of carbon-12. That's kind of a mouthful. And honestly, we're not going to use that definition for much of anything. I just pointed out here to show that that is the scientifically accurate definition of a mole. The way we're going to use it and what we need to think of is simply that it's a counting unit for things like atoms and molecules and ions, and that a mole of anything is equal to 6.02 times 10 to the 23rd of that thing. That's what a mole is. If you have 1 mole of something, you have 6.02 times 10 to the 23rd of that thing. That's all that it means. And so it's the unit that we use to count really small things. And it is a really, 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 really big number, which means that we use it to count really, 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 really small things. So let's just get an idea for the number. So again, we see it here. The number was named after an Italian scientist named Amadeus Avogadro. And we can see it written out here. And we call it Avogadro's number. Is the 6.02, and we see the more digits for it here. So Avogadro's number, 6.02 times 10 to the 23rd. Let's see it written out. So if we have 620,000, or sorry, 602,000 times a million, times a million, getting there. Now times another million. So here it is all written out. It's a huge number. It's ridiculously big. The reason I like to point out just how huge the number is, and by the way, in comparison, if you count up stars in the sky, there's something like 10 times 10 to the 10th. And so 10 zeros is going to bring us to about here. So if we put a 1 somewhere in this neighborhood, that gets us to stars in the sky. Keep going. Several places, several decimal places, and that brings you to a mole. It's huge, 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 huge number. I like to point out just how big it is, because if we think, for instance, about the amount of water that's in my water bottle here, there's more or less, and I'd have to go back and double check, but I'm pretty sure if I remember right, there's more or less about 20 moles of water molecules just in this bottle. 20 times this number here. 20 times Avogadro's number. It's just the number of water molecules in this bottle. So think about that for just a second. How ridiculously, cannot even wrap your head around it, tiny does a water molecule have to be if 20 times this number fit in here? Molecules and atoms are small. They really are so small that it really is beyond our comprehension to even think about how small things like that are. Incredibly, incredibly, incredibly tiny. And so sometimes people call the mole the chemist's version of a dozen. And so, for instance, if we're counting things like socks, eggs, pencils, paper, beer, atoms or molecules. Then if we're thinking about the number of socks, we think about those in terms of maybe pair of socks. And we know that one pair equals 2. If we're counting eggs, we'll probably count in terms of a dozen. How many dozen eggs do you have? And everybody knows that a dozen means 12. Pencils, we might be buying bulk pencils for a school. So we'll maybe think in terms of how many gross of pencils do we need. We know that there are 144 of anything, in this case pencils, 144 pencils in one gross. Paper, we think in terms of reams, 500 sheets of paper in one ream of paper. We buy beer, so oftentimes in cases. We know there are 24 cans of beer, bottles of beer in one case. Atoms or molecules, same idea. 6.02 times 10 to the 23rd atoms or molecules or ions in 1 mole. And so that's all it is. It's a counting number. And this here just gives you an idea for what that starts to look like. And so if I have 1 mole of copper ions, then I have 6.02 times 10 to the 23rd copper atoms. And that's going to take up, you can see, about 1/3 or so of this 50 milliliter beaker. And you see the hand here for a size reference to show you about how much that is. Or if I have 6.02 times 10 to the 23rd grams or atoms of sulfur, you can see how much space that takes up, and magnesium, tin, silicone, and so forth. And so in each of these beakers, there are 6.02 times 10 to the 23rd atoms of that particular element within that beaker. That's what a mole is. And so one of the big ways that we're also going to use a mole is with this idea of molar mass. Remember when we introduced the idea of atomic weight a week or so ago, and we were using these sort of ambiguous units of AMU. And so, for instance, we would look up on the periodic table, and we would find that the atomic mass of something like carbon, for instance, is 12.01 AMUs. And so we were using that before just to illustrate the idea of atomic mass and to look at isotopes and how we calculate the blended atomic mass that shows up in the periodic table. It's now going to take on some real meaning for us. So we just looked at carbon, with what we said, we looked on the periodic table, 12.011 atomic mass units. What that really means for us and the power, so to speak, of atomic mass and the way that we're going to use it is by now recognizing that what this really means is that there are 12.011 grams of carbon in every 1 mole of carbon. And so that's what we mean when we say molar mass. What is the mass of 1 mole of this element? And that's one of the big ways that we're going to start to use the periodic table, is by no longer thinking of these atomic masses in terms of AMUs. AMUs don't really do much for us, but we will start thinking of these in terms of atomic mass. And so my cursor's right on iron. This means that if I have a mole of iron atoms, that mole of iron atoms is going to have a mass of 55.845 grams. We abbreviate mole, MOL, by the way. Oh, sorry. There we go. We abbreviate mole, MOL, and so 55.845 grams of iron per 1 mole of iron. We're going to use this quite a bit. This is going to be one of the more common conversion factors. There's that word again. This is going to be one of the more common conversion factors that we use in converting back and forth between grams of something and moles of something. And we'll take a look at that in just a second. And so along with the molar mass of elements, sometimes we might be interested in the molar mass of an entire compound. So let's say we want to know the molar mass of sodium chloride. Well, we look on the periodic table, and we see that sodium has a molar mass of 22.990. And then we see that chlorine has a molar mass of 35.453. And so then we simply add those up. And we would get a molar mass of sodium chloride of 58.443 grams per mole. Now, maybe we have more than one of each element. That's fine. We just add those up. Let's say we're trying to find the molar mass of glucose. C6H12O6. Again, we're going to use the periodic table to find these atomic masses. But we look at carbon, and we see that we have 6 carbons times a molar mass of carbon of 12.01. Hydrogen, we have 12 hydrogens times a molar mass of 1.008. Oxygen, we have 6 times 15.999. And now, in answer to the question that some of you might have right now, no, you don't have to memorize atomic masses. You're always going to be able to use the periodic table. But just by using some of these so much, you will just end up remembering some of them. I mean, you're probably going to end up memorizing carbon, oxygen, and hydrogen. So we use them so often, maybe even nitrogen, just because we use them quite a bit. So you probably end up just remembering them from repetition. But you don't have to memorize them. You will have a periodic table available. But so then there's a couple ways that you could approach doing this calculation. You could either just do the math out of all of these. So we get 6 times 12.01. We're going to get 72.06. 12 times 1.008. 12.096. And 6 times 15.999. And we get 95.994, and then we can add those all up. And we have a molar mass of glucose of 180.15. Now, depending on how comfortable you are with your calculator, you could also simply type that in all at once. There's no reason that you couldn't do 6 times 12.01 plus 12 times 1.008 plus 6 times 15.999 equals our 180.15. Especially if you have a TI calculator, one like this, and you can actually see all of it as you type it in, then you can certainly do it like that. Or you can just do them all out separately like I did here, and then add them up. Either way, it's going to come out to the same, whatever you're more comfortable with in how you use your calculator. And so that's molar mass. And so here we have just the molar mass of several different compounds. We have some aspirin here, which is C9H8O4 with a molar mass of 180.2. Copper 2 chloride dihydrates. We're not going to talk about hydrates much. But hydrates are compounds that have water molecules stuck to them. In this case, each copper chloride molecule, or each copper chloride unit, has 2 water molecules attached to it. And so the molar mass of this copper 2 chloride dihydrate includes the mass of those 2 water molecules. And so just keep that in mind if you're ever working with hydrates. Then we have iron 3 oxide, Fe2O3. This is our molar mass there. So again, that's just the mass of 2 irons plus 3 oxygens all added up. And then water, with a molar mass of 18.02. So we can find the molar mass of just elements by using the periodic table, or the molar mass of an entire compound by simply adding up all of the masses of the elements in that compound. And so like I said, what this does for us, one of the things that molar mass does for us is it gives us conversion factors that we can use to go back and forth between the mass of an element or a compound and the number of moles of that element or compound. And so for instance, let's say that we have, or we know we have, just to throw a number out there, we know we've got 1.85 grams of aluminum. 1.85 grams of aluminum. And we want to know how many moles of aluminum that is. So we're going to take our 1.85 grams of aluminum, and now we're going to use our molar mass as our conversion factor. Oh, that's not the one that I want. Where's my periodic table? There it is. So here's aluminum. Let me just write this over here. So aluminum is 26.982. There are that many grams of aluminum per 1 mole of aluminum. Now remember that conversion factors can be written either way. We can either write our conversion factor in this form, or there's no reason we can't write 1 mole of aluminum per 26.982 grams of aluminum. And so we're going to use our conversion factor in whichever way that we need to for our units to cancel out that we want to disappear and to be left with the units that we're looking for. And so that tells us that we want to use this form of the conversion factor here for molar mass. That way our grams will cancel out and we'll be left with moles. So 1 mole of aluminum per 26.982 grams of aluminum. And again, we can see grams of aluminum will cancel out. We'll be left with moles. And this tells us then that into our calculator, we're going to have 1.85 divided by 26.982 to give us an answer of 0.0686 moles of aluminum. Note the significant figures there as well. 3 significant figures in our initial measurement, 1.85, 3 significant figures in our answer. So we have to always be keeping those in mind. And so this is just a conversion factor to go back and forth between grams and moles of aluminum. Similarly, Avogadro's number is also just another conversion factor. It's an ugly 6. Let me redraw that. 6, there we go, 0.02 times 10 to the 23rd. In this case, we'll say we're working with atoms per 1 mole of atoms. And so we could write that either way. 1 mole of atoms per 6.02 times 10 to the 23rd moles of atoms. So again, depending on what we're trying to do, let's say that we know we have 1.2 times 10 to the 24th atoms of sodium. And we want to know how many moles that is. So we're going to start with our 1.2 times 10 to the 24th atoms. And we know then that we want to set up our conversion factor so that we have moles of sodium left over. We have 6.02 times 10 to the 23rd atoms. We plug that into our calculator. We have 1.2 times 10 to the 24th divided by 6.02 times 10 to the 23rd. And we have an answer of 2.0 moles of sodium. Just a conversion factor. That's all that they are. You could even go, let's say we wanted to go further with this one. We'll use our same example, but our 1.24 atoms of sodium. We want to know how many grams that is. Just take the conversion factors further. Sorry, it was 1.2. Sorry, let's just use, well, we'll use this one. Why not? 1.24 atoms. No, sorry. Let me back up. Not 1.24 atoms, because that's a ridiculously small amount. 1.24 times 10 to the 24th. Forgot that very important factor there. So we have our 1.24 times 10 to the 24th atoms of sodium. We want to get to grams. we can't go directly from grams to atoms, but we do know if we go through moles, then we can use our atomic mass to get there. So the first thing that we're going to do is we know that there are 1 mole of atoms per 6.02 times 10 to the 23rd. Or sorry, there's 1 mole of sodium per 6.02 times 10 to the 23rd atoms. And then we're going to use our atomic mass. So now atoms is canceled out. We're left with moles. So we're going to use our atomic mass. We know we're going to want 1 mole of sodium down here. We look on the periodic table, 22.99 grams of sodium in the atomic mass. And so now we can just plug all of that into our calculator. 1.24 times 10 to the 24th divided by 6.02 times 10 to the 23rd times 22.99, and we get 47.4 grams of sodium. We're just using these as conversion factors. Now, if you really don't like dimensional analysis, and that's okay if you don't, I really love it as a problem-solving tool, but it doesn't work great for everybody. You could also memorize a chart such as this. This gives you all of your different mole conversions and tells you what to do and what to use to get there. Notice moles are at the center of this whole thing. Moles are central to these calculations that we're going to be doing and spending some time on. And so a lot of different calculations that you do, you're going to have to go through moles in some way. And so here we can see that, for instance, if we have grams and we want to get to the number of moles, the conversion factor we use is molar mass, and we're going from grams to moles, so our arrow is going this way, so we're going to divide our grams by our molar mass. Likewise, if we're going from moles to grams, so we're still using our conversion factor of molar mass, but we're going to multiply by molar mass now to get to grams. If we want to go from moles to the number of atoms or molecules, then we're going to use Avogadro's number and we're going to multiply. From atoms or molecules to moles, we're going to divide by Avogadro's number. This also shows you how you can go from grams to atoms or molecules. First, you're going to divide by your molar mass to get to moles, and then multiply by Avogadro's number to get to the number of atoms or molecules. You'll also see molarity down here. Molarity is going to be a large portion of a large topic of our next lecture. But I include it on this slide here because it's going to be another central calculation, and a chart like this is going to be very useful for a lot of calculations that we do all through the semester. So don't necessarily worry about molarity just yet. We will be talking about that next week. And so like I said, you could either memorize and know how to use a chart like this and just know, okay, I'm going from grams to moles, I divide by my molar mass. I'm going from atoms to moles, I divide by Avogadro's number. I mean, that's absolutely fine if that's more the way your mind works to sort of memorize things like that. Or, again, just recognizing that that everything's a conversion factor. You can set things up that way. I typically always use the conversion factor approach, and the examples that I use in lecture, I'm going to be using these as conversion factors. And so this just goes through a lot of what I was just showing. So here we have a mass to moles conversion. We're going to take our 16.5 grams of carbon, and we're going to multiply that by our molar mass, we're going to divide it by our molar mass to get to our 1.37 moles of carbon. You'll note the number of significant figures, that there are 4 in our molar mass conversion, but our initial measurement, again, only had 3. So there are 3 significant figures in our final answer. You always want to use as many significant figures in molar mass as whatever periodic table that you're using gives you. And so molar mass typically will not be the deciding factor in your significant digits, because you're usually going to be using a resource such as the table here. You can see how far out most of these go. Most of these are going out to the thousandth spot. And so they mostly have 5 significant digits there. you're not going to be working with many measurements that have 5 significant figures. And so usually the actual measurement, it will be your deciding factor. So just keep that in mind. Okay. And here's just some practice. And so see if you can do this one. Go ahead and pause the video now and see if you can calculate how many magnesium atoms there are in 150.0 grams of magnesium. And so pause the video now and we'll see how you did. Did you get it? And so remember your solution, you're going to use the molar mass of magnesium. You're going to use Avogadro's number. And so we can see the conversion factors set up here. We're going to first take our 150.0 grams and use our molar mass. And then we're going to use Avogadro's number, and you can see how everything is canceling out. Our grams cancel out here using molar mass, then our moles cancel out using Avogadro's number, and we're left with 3.717 times 10 to the 24th magnesium atoms. Note that this is a huge number, times 10 to the 24th. And so this is a phenomenally, really big number. I point that out because it's important to think about sort of the size and scale of your answers and think about if they make sense. You're being asked here to calculate how many atoms there are in a particular sample. Your number better be huge. We know that atoms are incredibly tiny, and so we're going to have a huge number of them in any given sample. And so if you are working on a question and it's asking you for the number of atoms, and you come up with 4, or 6.2, something like that, you did something wrong somewhere. You probably forgot the exponent somewhere along the way. And so just take those few seconds and think about, does the scale of my answer make sense here? Likewise, the opposite is true. If you're trying to calculate mass and you come up with something, 4.2 times 10 to the 26th, that's obviously way too huge. And so something went wrong somewhere. So think about what you're calculating and the scale of the number that you get, and make sure that it actually makes sense. So again, here's another example. So how many grams of chromium are there in 25.1 grams of chromium-3 acetate? Do the same thing. Go ahead and pause the video, try to run through this calculation and see what you get. And we're back. So you can see the first thing that you have to do, is to come up with your formula even for chromium-3 acetate. And so again, we're seeing the importance of knowing your polyatomic ions. You have to be able to come up with a chemical formula. Chromium-3 tells us that we're dealing with a chromium with a 3+ charge. Our polyatomic ion acetate, C2H3O2, has a -1 charge. And so we come up with this formula here, which we then use to calculate our atomic mass. So remember, as you're calculating this number, if you did not get this, you might have missed the subscript 3 or done something incorrect there. We'll just take a quick peek at that. So again, our formula here is Cr C2, H3O2, and we have 3 of those. So as you're calculating your atomic mass, you're going to have 1 Cr atom, and then looking up the atomic weights, whatever those are, just again, look on the periodic table for those. But then for these others, so we have C2H3O2, and so in 1 acetate ion, you have 2 carbons, but you have 3 acetate ions, each of those with 2 carbons. And so you're going to have 6 carbons here. Each acetate ion has 3 hydrogens, times 3 acetate ions for 9 hydrogens. And then each acetate ion has 2 oxygens, times 3 acetate ions for 6 oxygens. And so that might have been where your error was if you did not get the same molecular mass. So go back and check that. So then we're going to take our 25.1 grams of chromium, and we're going to then multiply that by our molar mass of chromium acetate. But we want to know here just how many grams of chromium there are. And so the other important conversion factor to note is that for every 1 molecule of chromium acetate, we have 1 molecule of chromium, which means that for every 1 mole of chromium acetate, we have 1 mole of chromium. So we need to do that conversion. We need to go from chromium acetate to just chromium. And then our final step, the question is asking us for grams of chromium. So now we're going to go from, there we go, moles of chromium to grams of chromium by using our molar mass of chromium. So we find that in that much chromium acetate, we have 5.70 grams of chromium. So a lot of steps here. If you're still a little fuzzy on that, just go back through, make sure all these conversions make sense to you, and why we're using what we are, where we're using it, and why we're using these conversion factors in the form that we are, and just really make sure that this makes sense. Here are several other practice questions with the answers. And so you've got the answers right here. I would definitely go through all of these, make sure that you can come up with the right answers. If you can't, go back and follow through the same process. Feel free to email me if you're having trouble getting some of these answers. Maybe go to a tutor. We haven't talked about the Learning Commons much yet, but I'll be talking about that in an email a little later. But absolutely, these are questions that tutors could help you with as well. So here's another example. So we have the average daily dietary requirement of an essential acid leucine. We have the chemical formula there, is 2.2 grams for an adult. So we should be getting this much leucine in our diet every day. And so a few different calculations. You want to calculate through and find out how many moles of leucine are actually required. And then figure out how many molecules of leucine that actually equates to. And then figure out how many nitrogen atoms are present in that amount. See if you can do those calculations. And then finally, how many carbon atoms. So see if you can do those. Calculate those on your own. If you want, go ahead and send me what you think the answers are, and I can tell you if you're right. So now we come to this other idea of percent composition. The percent composition is an analysis which we can use to characterize unknown compounds. And it can be used to calculate what we call an empirical formula, which we'll be talking about in a little bit. The percent composition is simply the mass percent of each element in a compound. And so we have sort of the strategy of it here. We take the number of atoms of an element, we multiply by the atomic weight, we divide that by the formula weight, and we multiply by 100 to convert it to a percent. Now that seems kind of complicated a little bit if we think about it like this. But let's take a look at these examples. So if we want to know, for instance, the percent composition of all the atoms or all the elements in calcium hydroxide, CaOH2. So first we're going to focus on calcium. And so we take our calcium, we have 1 calcium atom in there. We multiply that by 40, that's the molar mass of calcium. We divide that by 74.1, which is the molar mass of calcium hydroxide. We multiply by 100 to convert to a percent, and we get 54.0%. And we can likewise do the same for oxygen. We do the same thing out, but we have to note that there are 2 atoms of oxygen, noted by our subscript 2 after a hydroxide. And we get 43.2, and likewise for hydrogen, 2.72. Let's see what this actually looks like, though. Let's do this out slightly differently. So here's our chemical formula, CaOH2. Let's calculate the molar mass of CH2 in one of the ways that I showed you. So our calcium, we have 1 calcium atom in there. And the molar mass of calcium, let's pull up our periodic table. Our molar mass of calcium is 40.078. Oxygen, we have 2 oxygen atoms times a molar mass of 15.999 gives us 31.998. Hydrogen, we also have 2 times a molar mass of 1.008, 2.016. So just like we were calculating molar mass before, we're going to now just add those up. So we get 40.078 plus 31.998 plus 2.016. And we get a molar mass of 74.092. Now, all you have to do, sorry, I didn't switch over there, but there's everything I was just writing. All you have to do now in order to calculate the percent composition of each element is just take each one and divide it by the total. So calcium, the contribution of calcium was 40.078. And so we're going to go ahead and divide that by the 74.092. We're going to multiply that by 100 to convert it to a percent. Sorry, let me try to get rid of this little. There we go. Multiply by 100 to convert it to a percent. So 40.078 divided by 74.092. And we're going to get 54.1%. Oxygen. Its contribution was 31.998 divided by our total, 74.092 times 100. (43.2%), and then finally hydrogen, 2.016 divided by 74.092. 2.72% hydrogen. So that's all percent composition is you're dividing the contribution of each element to the mass by the total molar mass of the whole thing. It's always good when you're calculating a percent composition to do a final check at the end as well. Add them up. They should add up pretty darn close to 100. Any differences would just be some differences in rounding along the way. Maybe a molar mass that was rounded a little bit differently, something like that. So 99.92, we're pretty much there at 100%. But again, here's a quick check, because if you're getting 72 or you get 145, something went wrong along the way, and you should go back and check it. So do those final checks just to make sure that your answers make sense. And so really the last big thing to talk about today is an empirical formula. A molecular formula, we've talked about molecular formulas already. Molecular formulas show us the actual composition of a molecule. How many of each type of atom is in the distinct molecule that we're talking about. An empirical formula only shows us the simplest ratio of those atoms. Ionic compounds, for instance, are always represented by their empirical formula. Remember how I showed you that ionic lattice when we were discussing ionic formulas? That ionic lattice, or the formula that we give, shows us the simplest ratio of atoms within that ionic lattice. So an ionic compound is always going to be an empirical formula. Covalent compounds aren't necessarily, because covalent compounds will exist as discrete molecules with their particular molecular formula. And so as an example, let's take a peek. Remember our formula for glucose that we've looked at a couple of times. Our chemical formula for glucose is C6H12O6. That is our molecular formula. And so a single molecule of glucose absolutely consists of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. The empirical formula for glucose is going to be the simplified version of this. And so we could break this down to its lowest whole number ratio by dividing each of these terms by 6. So if we divide each of these by 6, then we get CH2O. That is now our empirical formula for glucose. And so it's our simplest whole number ratio. Now, it's important to keep in mind that this is the form in which glucose actually exists. Glucose molecules will exist in this ratio. The empirical formula is useful, though, because there are analyses that we can do, and we'll talk about some of these analyses a little bit later as well. But there are various analyses we can do if we have a completely unknown compound. If somebody gave us a sample of glucose, but we didn't know that it was glucose, there are experimental procedures that we can perform that will return the empirical formula to us, that will allow us to calculate the empirical formula. From there, we could scale up using some other experimental procedures to find the molecular formula. So we could take something that is completely unknown, so a compound that we don't know what it is, and as long as we can perform these analyses on it, we can find the molecular formula of this unknown compound. But we have to go through the empirical formula to get there. And so that's why it's important for us to know what empirical formula is and how we can use it. So think about some of these. Think about if these are examples of an empirical formula, molecular, or in some cases it might actually be both. So H2O. Can we simplify that at all? Is it empirical or molecular? H2O2. Empirical or molecular, HO, sorry, and C6H12O6, our glucose. So H2O, we know that's the formula for water. And so that is both the empirical and the molecular formula. You can't simplify it anymore, but we know that it is the molecular formula for water. H2O2, hydrogen peroxide. That's the that's the molecular formula. That could be scaled down to just HO, which would then be its empirical formula. HO, the third example, that's simply an empirical formula. We would not consider that to be both because there aren't any compounds, so to speak, that are going to have that formula. There is the polyatomic ion hydroxide, but that's a little bit different of a situation. And finally, glucose, C6H12O6, molecular formula, because we could scale that down to an empirical as we were just showing. So how can we get there? How can we actually derive an empirical formula? We're going to go through these various steps here. We're going to take our first step, and what we do is we take our percent by mass. So the mass percent that we were working with a few minutes ago, we're going to use that, and we're going to take the mass percent of each element, and the first thing that we do is we convert that to a mass. What we do is we simply assume that we have 100 grams of a substance. Makes it an easy number to work with. And so if there's an element that, for instance, is 63% by mass of this compound, then we just convert that 63% to 63 grams. Our next step is to convert that number of mass to moles by using the molar mass. And so we're going to convert to the number of moles for each element in there. Then we find the mole ratio. When we find the mole ratio, and we're going to look at a few examples of this, so don't worry. When we find the mole ratio, what we're going to do is take those number of moles that we found in step 2, and we're going to divide each one by the smallest number of moles that we found. And then we convert to whole number ratios, and we'll see what that means. Let's look at an example here. So here we have methanol. Just shrink this down for us so we can bring up the whiteboard, look at some things side by side. All right, so we have methanol. Is 37.48% carbon. Oh, sorry. Going nuts on me here. Here we go. Methanol is 37.48% carbon, 12.58% hydrogen, and 49.93% oxygen. And so these are just the mass percentages of methanol. And so we want to know what the empirical formula of this is. And so, like I said, the first thing that we're going to do is we're just going to take those percentages and we're going to convert those over to masses. And so we're going to say that what we actually have is 37.48 grams of carbon. And we've got 12.58 grams of hydrogen and 49.93 grams of oxygen. What we're going to do next, step 2, is just to convert all of these to moles. And so we're going to use our molar mass. So 1 mole of carbon, we look on the periodic table, 12.01 grams. And we plug this in and we get 3.12 moles of carbon. Hydrogen, 1 mole of hydrogen to 1.008 grams of hydrogen gives us 12.48 moles of hydrogen. Then finally oxygen. For 3.12 grams of oxygen. So there's step 2. Now we've converted all of these to moles. Now what we're going to do is take each of these mole numbers here. So each of these moles that we've calculated, we're going to take and divide each of those by the smallest one. Now the smallest one in this case is equal for 2 of them. So our smallest number here is 3.12. So we're going to divide each of these by 3.12. There we go. Sorry. So 12.48 divided by 3.12 equals 4. And so we get 1, 4, and 1. These numbers that we've just found, these are now our subscripts for our empirical formula. And so for C, we found a subscript of 1. For H, we found a subscript of 4. And for oxygen, we found a subscript of 1. And so our empirical formula for methanol is going to be CH4O. There it is. That's our empirical formula. Those are just the steps that we used. We simplified our mole ratio. And this is just a note that hydrocarbons, we typically write in this format of our carbon, hydrogen, and oxygen in that order with the appropriate subscripts. So another example here, magnetite. Magnetite is composed of only iron and oxygen, and we know that it is 72.36% iron. We're not given any information about oxygen, but that's easy enough to find. We know that this is only composed of iron and oxygen. And so the amount of oxygen has to be 100% minus the 72.36. And so we have 27.64% oxygen. Now we're going to take our same steps. We're going to take our 72.36% and convert that to grams of iron. Our 27.64% and convert that to grams of oxygen. Now we're going to convert that over to moles. 1 mole of iron, 55.85 grams from the periodic table. We get 1.30. 1 mole of oxygen, 15.999 equals 1.73. Now we divide each of those by the lowest whole number. The lowest is 1.3. So we get 1.30 divided by 1.30 equals 1. 1.73 divided by 1.30 equals 1.33. Now we know we can't really use that 1.33. That doesn't make a lot of sense, but let's just put it in as a placeholder to start. So we get Fe1O 1.33. We know that formulas, empirical formulas or molecular formulas, have to consist of whole numbers for their subscripts. We can't have these decimal points. And so when you come to a situation like this, what you want to do now is scale up by the appropriate scale factor to just get you to whole numbers for each one. We can see here that if we multiply 1.33 by 3, that's going to get us to a whole number. And so we're going to go ahead and multiply both of these through by a factor of 3, which then brings us to Fe3O4, and there's our empirical formula for magnetite. Not that bad, right? Now, you might sometimes find these mole ratios, I mean, you could very well come up with something like 5.98, then, okay, you're just gonna round that to 6, or 1.97, that's gonna round to 2, you know, 5.02 will round to 5. I mean, it's things like that that are really close to a whole number. That's pretty obvious, you can just round to that. But if you have something like this, like a 1.33, then okay, you're gonna scale up by 3. If you have 2.25, scale up by a factor of 4, and so on to get to your whole numbers. So those are the steps that we went through. We multiplied by our 3 to get to our Fe3O4. So here's just another example here, probably written out a little bit neater than what I'm trying to write on my whiteboard. But here we have a compound, 64.82% carbon, 21.59% oxygen, 13.59% hydrogen. And we want to find the empirical formula. So we go through the same exact process. We're going to convert each of those percentages to grams. We're then going to convert each of those grams to moles. This is the same thing that I did on the whiteboard. We just see it here all typed out, nice and neat. So there's our 64.82 grams of carbon converted to moles, our oxygen converted to moles, our hydrogen converted to moles. We divide each of those now by the smallest number, which is 1.349. So the first one is going to get us our subscript for carbon, and then our subscript for H, and then our subscript for O. And this is what I meant here by some that are going to be obvious that you can just round to the nearest number. I mean, 4.001 is going to round to 4. 9.992 is obviously going to be 10. And so our empirical formula for this compound is going to be C4H10O. And there's our empirical formula. Now, we might have some cases where once we find the empirical formula, we also might be given information to calculate the molecular formula from that. And so to find the molecular formula, you would have to be given the full molar mass of the compound in question. And so since, remember that molecular formula is a multiple that's scaled up by a factor of n. So you might have an empirical formula that is half what the molecular formula is. And so that would be a molecular formula scaled up by a factor of 2 from the empirical formula. And so let's look at that a little bit more clearly. Sorry. Whoa, there we go. Okay. So here's the compound that we were just working with. And we said that let's go back a little bit. We said that we calculated the empirical formula of this compound to be C4H10O. Now we're also given some additional information right here. So when we calculate the empirical formula weight, so the molar mass from the empirical formula, we're going to take, just the way that we've been doing molar mass, our carbon is 4 times 12.01, our hydrogen 10 times 1.008, our oxygen 1 times 15.999. We add those all up and we get a formula mass of the empirical formula of 74.12. So that's the molar mass of just the empirical formula. We're also given some extra information here in that the molecular molar mass, so of this actual molecule, if we knew the molecular formula, we're told that the molar mass of that is equal to 222.1. So what we can do now is we can take our molar mass of the whole thing, our 222.1, we divide that by 74.12. That's going to tell us how much we are scaled up by as we go from the empirical to the molecular. And so we plug that into the calculator, 222.1 divided by 74.12, and we find 2.996. We find basically a scale factor of 3. That tells us that as we're going from the empirical formula, our C4H10O, remember that this is our empirical, that we want to then scale that up by a scale factor of 3 to get C12H30O3. And that is now our actual molecular formula of this unknown compound. So you would have to be given this additional information. You would have to also be told what the molar mass of the whole unknown compound is. You have to have that in order to scale up from the empirical to the molecular weight. C12H30O3. Let's look at this last practice problem. So hexamethylenediamine, sounds fancy, really isn't, but it's a material that's used in the production of nylon. And we have this elemental analysis. We know that it is 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. First thing we want to do is find the empirical formula. So we're going to do that the same way that we've been doing. We're going to take our 62.1, we're converting those to grams of carbon, so this is the same thing that we've seen a few different examples of. 13.8 grams of hydrogen, convert that over to moles. Now we're going to divide each of those by the lowest amount. So we'll take our 5.17 divided by 1.72, 13.69 divided by 1.72, and 1.72 divided by itself. And so that's going to now give us our empirical formula. And so our empirical formula for this is going to be C3H8N. So let's just go to another page. And so we just found our empirical formula to be C3H8N. We're also told that the molar mass, the molecular weight of the whole entire compound, is 116 grams per mole. So we want to do the same thing that we just did. We're going to find the molar mass of our empirical formula. We add those all up, and we get a molar mass of 56.68 grams per mole. We're told that our molecular mass, remember our molecular weight now, is 116. We'll divide that by our 56.68. And we get an answer that's pretty darn close to 2. It's a little bit less than 2, but pretty much right at 2. This tells us that our scale factor to go from our empirical to our molecular is a scale factor of 2. And so our molecular formula then for hexamethylenediamine, forgot what it was. We're going to scale everything up by 2. We get C6H12O3. H16, N2. And there it is. And sure enough, I bet you if we Google search for, you see I've already done it, hexamethylenediamine, we look it up here, we find our chemical formula, C6H16. Sorry, I have no idea why I wrote 12. There we go. Wrote 12, obviously meant 2. Sorry about that. Just a little erasing. There we go. C6H16N2. And that is our chemical formula. So, okay. A lot of information here. Well, a lot that we talked about today, with the central concept being the mole. The mole is absolutely our central concept in all, or in the majority at least, of chemical calculations that we do. And so we talk about a lot of things surrounding the mole today. In our next lecture, we're going to move on to solutions and how we look at amounts of things when they're dissolved in water. And so until next time, and as always, if you have any questions, definitely be sure to shoot me an email, hit each other up on Piazza, and so forth. Have a great day.